Hello everyone, my name is Serhan. I'm a researcher at Fraunhofer HHI at the Video Coding and Analytics department. In this talk, I will present our paper, Kalman filter-based head motion prediction for cloud-based mixed reality. Bringing mixed reality content to mobile end devices requires streaming of volumetric video in an efficient way. However, high-quality volumetric video is very complex, so rendering even a single volumetric object is very challenging on today's mobile devices. A solution for that is to offload the rendering to a powerful cloud server and transmit to the end device only the rendered 2D video stream, which is dynamically updated based on the user's head pose. A disadvantage of this solution is that the interaction latency increases significantly because of the added network and video compression delays. In the diagram, we can see the latency components of a cloud-based rendering system. After the current user pose is sent to the server renders a view meshing to that and encodes a 2D video from that view. This view is then transmitted to the client over a network, which decodes the frame and displays it on the end device. Compared to the local rendering system, the new latency components are the encoder latency, T-eng, and the network round-trip time, which is the sum of propagation and transmission times over the network, T-up, T-down, and T-trans. A promising approach for reducing effective latency that we investigate in our work is to predict the user's head pose at the cloud server and render the corresponding view of the volumetric content in advance. So head motion prediction was previously investigated for optimized streaming of omnidirectional videos by predicting the user's future viewport and streaming that in advance. Many different approaches exist in the literature that rely on different techniques to predict the user's viewport. However, these methods so far only looked into the prediction of head orientation with 3 degrees of freedom for VR and did not consider 6 of prediction, including the translational movements. In our work, we developed a Kalman filter-based predictor that predicts both the position and orientation of the user in 6 of. And we integrated this predictor into our existing cloud server architecture. So at each sampling time, the HoloLens records the user's head pose and sends the measurement ZK to the cloud server. The Kalman filter then combines the incoming measurement with the previous state vector and outputs a state estimate, which is propagated multiple time steps ahead to obtain the predicted pose for a certain look-ahead time. This predicted pose then goes into a renderer module, which renders the corresponding view from the volumetric content. This view is then compressed using a hardware video encoder and sent over the network with low latency using WebRTC. On the client side, the mobile device decodes the video, integrates the virtual object into the scene by removing the background, and finally displays to the viewer. To evaluate the performance of our predictor, we created a HoloLens application and collected head motion traces from 14 users while they were viewing the object from different angles and distances. We recorded the user position and orientation at each time point and used the obtained traces as input to our predictor. Then we computed the mean position and angular errors for different look-ahead times ranging from 20 to 100 milliseconds. We compared the results to an autoregression model from our previous work that used a linear combination of the past values and to a baseline model which does not perform any prediction. Our results show that in terms of the position error, both autoregression and Kalman filter perform better than the baseline, while for orientation, only the Kalman filter reduces the angular errors significantly, on average varying between 0.3 to 0.9 degrees depending on the look-ahead time. So to summarize, we developed a Kalman filter-based predictor that reduces the interaction latency. And our approach can predict the head orientation of the user better than a benchmark model. It needs no previous training and is also more robust to variations in different traces. In our future work, we will use recursive filters based on spherical distributions in order to reduce the angular prediction errors even further. Also, we'll perform subjective tests to understand the effect of interaction latency, as well as prediction errors on the subjective experience of the viewers. So for more details, feel free to check our ACM Multimedia papers And please contact us if you have any questions. Thank you.